right, welcome back. We're going to continue with our lists and list-based data structures lectures. We already covered array-based lists. Now what we're going to want to do is we're going to want to, first of all, we'll finish up by thinking about some other functionality that we could do. For example, we could clear the list. We could find a way to shrink the list if its capacity is too much, right? Because we were growing the list before. When it hit the capacity, then we made it a slightly bigger. We could go ahead and tweak that, right? Instead of going up by tens, we could go double the size or something, right? We could have a way to add multiple elements, right? A batch add. This entire array, go ahead and add everything to the end or append everything to the end. This entire other list, a copy of a list, go ahead and do that. We could have a way to do a copy constructor where I want a deep copy. Here's a list. I want a completely separate deep copy of this list, and we can do that through a copy constructor. We could do basic search algorithms. We could do a find a particular element. We could insert at the beginning. In fact, we already have that functionality. All you need to do is specify an index of 0, and you can always insert at the beginning. But of course, you could make that into a function with a proper name of insert at beginning or something. Okay. Anyway, those are some other pieces of functionality that I'll invite you to try out and implement yourself. What I wanted to show you is that this is not always the best answer, right? So for example, if we want to insert 100 things, I'm always going to go ahead and insert them at the beginning. So let's go ahead and run that. And I'm timing this, and it didn't even take a registerable amount of time, right? Let's go ahead and bump that up to 1,000. There we go. So 1,000 elements being inserted. Remember now what we're doing is that eventually there are going to be 500 elements here. And what we're going to do is we're going to insert one at the beginning, meaning that we're going to have to shift 500 elements down. So let's go ahead and run this. And now we get that it's a registerable amount of time. It's going to be 5,000ths of a second, okay? So let's bump that up by another factor of 10, right? So 10,000 here. Now, if this were, it's 10 times as big, so I'm thinking it's going to take 10 times as long, right? In other words, it will take 0.05 seconds now. But it doesn't. It takes orders of magnitude, not orders of magnitude, but it takes way longer than that, right? Let me go ahead and bump this up again. That if we went from 10,000 to say, let's make it simple, 20,000, right? That's twice as big, so it might be twice as long, right? 0.3 seconds is my estimate here, but it's not, right? It's even more than that. And what you'll do is you'll find a pattern here that if we bump this up to 40,000 here, it's not going to be 5 seconds. It's actually going to be 4 times as big. So 4 times, twice as big. So not 1 second, but 4 seconds here. That's going to be my actual estimate here. 4 seconds, 2 seconds, way more than 1 second here. So let's kick this up to 100,000 here and see that it's actually going to take almost 10 seconds here. While we wait for that to execute, what if I change this, 12 seconds. What if I change this so that I was always adding at the end? So now why was it so slow? Because when I got up to 50,000 elements, right? I was shifting 50,000 elements down to make room for that element at the first index. I was doing 50,000 operations. On the next operation, I was shifting down 50,001 elements, 50,002 elements, 50,003 elements. So all those operations start to add up. But if I do it at the end, it is way quicker, right? That is, 1/20th of the time that it took me to do, to insert everything at the beginning. Why? Because I was not shifting everything down, right? I was just adding it to the end, adding it to the end, adding it to the end. So, can we come up with an alternative list where some of these operations are more efficient? Right? And that's where we're going to explore today, linked lists, okay? There is no underlying array. Instead, elements are stored inside of individual nodes, right? Each node references an element and the next node, right? References, there we go, sorry. Each node is thus chained together or linked, right? That's why we call it a linked list. Basic operations involve traversing the list, okay? So let's go ahead and come over here and develop a linked list. Before we do that, let's go ahead and visualize a linked list, okay? So again, a linked list is going to have nodes, and I'm going to draw them as boxes here. Boxes separated by actually 2 elements here. So suppose that I wanted 42 in that box. 42 is being stored here. But this is a reference to the next box. And suppose that I've got, I don't know, 10 stored there. That's a reference to the next box. 20. That's a reference to the next box. And so on and so forth. I'll go ahead and make it as 30. What about the end of the list? All right, if we only have 4 things in this list, what does it look like at the end? I'm just going to go ahead and put a placeholder here, phi. In other words, as far as Java is concerned, this is going to be null. Some terminology here. This is the head of the list. This is the tail. We traverse it. If we wanted to like get an element, what we would have to do is we'd have to start at the head, and is that the thing that we're looking for? No. So we traverse over to the next one. We can do that because we have this relation here, this link, that we can go ahead and jump over to this node over here. We can jump over to the next node. We can jump over to the next node, next node, next node, etc. Right? That's the idea of a linked list. Now let's come over here and try to implement it. But before I do, what I want to do is I want to take a look at my array list again. Right? So this is great. What if I want a different implementation of a list? My linked list, for example. Immediately I'm going to start out with a parameterization. So my linked list. There we go. And I'll parameterize it according to t. Okay? So it looks kind of like this over here. I'm going to want to write the same basic functions. Add element, remove element. ToString, of course, everything has that. Get element at index, etc., etc. So what I want to do is I want to take a little bit more of an object-oriented programming approach to this, and I want to create an interface, a list interface, just like Java does. And what I'm going to do is I'm going to take out all of the functionality that I had over here and bring it over to the interface over here. But I'm going to clean it up because, of course, interfaces do not have implementations. They only specify the interface, right? The actual methods that are there, okay? So remove last element, there we go. ToString, I don't need to put that into an interface because everybody has that. That's Java. Every Java class has a ToString method. I'll go ahead and take out this implementation. I'll take out this implementation, take out that to-do, is empty, there we go, there we go, there we go, and keep continuing taking out implementations until I have a pure abstract class. There. There's my list interface, my list interface, right? So if we want to, we can rename this my list interface. And I will go ahead and rename this. There we go. I don't want to get confused with the Java list interface. Okay. Now let's come back over here to my array list, and we can say that this implements my list parameterized along the same element t. So that over here in the demo class, now I don't have to specify that this is my integer array list. I could say that this is my list of numbers of elements of integer type, right? And I will go ahead and create a new, what is it? My array list. There we go. Parameterize it along the same thing. And now it's looking a lot more like how you use this in Java, right? What type of list is this? I don't know, who cares, right? It's my, the implementation over here on the right-hand side is my array list, but I can actually go ahead and change that to my linked list once that implements that interface. So let's come over here to my linked list and say that it implements my list t. So this is subtype polymorphism inheritance in action here, right? It's not actually inheritance because you're not inheriting from an abstract class, but you are inheriting the interface from a pure abstract class. And now, do you know what type of list this is? Nope. But I didn't have to change any line of code in this entire thing. You can still add stuff at the end or at the beginning. Now, obviously, I don't have any implementation here, so let's go ahead and take care of that now. Okay. My linked list. I need to implement each one of these things. My first step is going to be to define the state of this class, right? And that's going to look something like this. Basically, I need these nodes here. I need a way to represent a node. So before we even get into that list, let's go ahead and create a new class called node. And it's also going to be parameterized along t's. Why? Because it's going to hold an element of type t. Right? So private, we can make it final, element of type t, element. There we go. Now it's final, so I don't have a constructor yet, but we will here in a moment. Okay. So that takes care of a basic node. Let's go ahead and zoom in on this basic node right here. Right. There's a node. This thing here is the element. Now what I need is a reference to another node. This is a node. Right. How do I do that in Java? Well, if you want a net reference to a node that holds elements of type T, call it the next. There we go. Private, final. Actually, I'm not going to make that final for a reason that will become apparent here in a moment. Okay? Okay, there's my node class. How do I put stuff into it? How do I take care of it? Well, first of all, I'm going to probably want a public node T element. There we go. And this dot element is equal to element. What about this dot next? If I just create a node like I did over here, right, and I put X into it, what do I want this to be pointing to? The next node, and in this case though, if there is no next node, what? What is the tail pointing to over here? Null. So let's go ahead and explicitly set that to null. You don't need to do that actually because the default is null. So, but I'll do it explicitly here for demonstration purposes. Probably want some other things. For example, public node T get next. Right. Why? Because you want to traverse nodes. If you start this node, you want to go to the next node. So if I've got a node, I want to get the next node. Return this dot next. Right. Probably a getter for the element. Public T get element. Return this dot element. Right. There we go. And that's pretty good for now. We'll come back and we'll develop this more as we need more. Okay. Now we can come over here to my linked list. Let's go ahead and take a look at this picture again. What do you need to keep track of every single node in this list? If you did, then where would you put it? Into an array. And you're right back at square one with an array list. Right? So no, I'm not going to keep track of every single node. I'm going to go ahead and focus on one node. The most important node here, the head. Right? Because I need a way to start the list. I'm going to start at the list. You can keep track of the tail as well. And we'll talk about that as an alternative or as an augmentation for this list. But for now, we're just going to go ahead and go with private node T first, or head, let's call it head because that's what it is. Okay. Now let's think about the constructor for this, my linked list. Public my linked list. There we go. So how are you going to initialize this? If you want an empty list, let's go ahead and look at a picture here. What would an empty list look like? Would you have a node with something in it? That's something. That's not nothing. So head is going to point to, if it's an empty list, what should it point to? Null. There you go. So I will simply make that this dot head is equal to null. What else might we want to keep track of here? What did we keep track of over here in my array list? The size. Let's do that as well. That's probably going to be convenient, right? I want to know, I want to keep track of how many elements are in here. Because whenever I add an element, I'm going to increment that. Whenever I remove an element, I'm going to decrement that. Right? Let's go ahead and start by putting stuff into it. Oh, and then, sorry, what should I initialize the size to? That's also the default 0. Right? So you don't need to do either one of these. So you could get away with not having a constructor, the default no argument constructor at all, but it's better to do this explicitly. All right, how are we going to add the element? Remember that this one is add it to the end. How are we going to remove the last element? How are we going to get the element at a particular index? How are we going to get the size? Well, that one's easy. This dot size. Let's take out that to do. Great. Is empty. That's also easy. Return this dot size equals 0. In fact, that's got me rethinking my design here, because if these are the exact same pieces of code as over here, right? In fact, they are. Maybe I should have not an interface, but an abstract class that takes care of these two default methods. But I'm not going to go that far today. Replace element at index. Okay. Remove element at index. Insert element at index. All right. So let's start with this one. Add it to the end. So let's go ahead and visualize this first. What if I've got that list that I had before, where I've got 42, and I'll make it smaller here, 10 and 20. There we go. It looks something like this. And this is going to be null, and this is our head, the head of the list. Now, if you want to insert it at the end, you're going to put it over here. You're going to replace this null here with, say, 101. Right? So how do we do that? Can we immediately, with the array-based list, can we immediately jump to the end of the list here? Nope. From the beginning, exactly. Start at the head, right? And now, are we at the end yet? Well, I'm checking the next node. Right? We're not at the end. So jump over to the next node. Are we at the end yet? Nope. So jump over to the next node. Now, are we at the end now? Yes. So now zoom in on this. How am I going to do this? First of all, let's go ahead and create that node containing 101. And it's pointing to null. Right? Now, what am I going to do? Yep. Take this. And instead of pointing to null, I'm going to now make it point to this. So let's go ahead and erase this and move this over here and get all of this. There we go. Come on. Undo. There. I'll move it over here. Null. There we go. Yeah, I put it at the end. Right? So that's our idea of this, okay? Let's go ahead and come over here and implement it. All right, so we need to get to the end of the list. Find the last node, ... Right? That sounds like might be a useful function, right? You might want to find the last node over and over and over again. Or you might want to find, say, an arbitrary node. You want to find the ith node, the 0th node, the first node, the 1th node, the 2th node, et cetera, et cetera. So before I even start this, maybe I should think more generally here, and maybe I should think ahead with my design and say, that's going to be useful. I'm going to use that all over the place. So find the last node. Let me go ahead and create a public first. Node t get node index I. Right? So let's document this. Returns the node at the given index. Okay. Oh, and then what am I doing? Index I. Index is what I want. There we go. All right. Now, before I implement this, let's think about this public here. should you be able to have access to all the nodes from the outside world over here in the demo class? Why? Are you going to, it's just a list. Should you have to worry about whether or not this is a linked list or an array list? Probably not, right? Did you have to think about arrays when you used that list originally? No, I don't want to force you to think about arrays. Therefore, I don't want to force you to think about nodes. Let me go ahead and make that private. You can still use it inside this class, right? But now you're not putting the burden on the outside world. Suppose that somebody could come in and just grab an arbitrary node and do whatever they wanted with it. That's bad encapsulation. Encapsulation is protecting your class and its state and behavior from the outside world, and only giving access to what they need. All right, let's suppose that we've already done that. I'll return null here, but don't forget it, right? To do, implement. All right, find the last node. So node t last is equal to this dot get node. Where's the last node? If I've got 5 nodes in there, it's at 0, 1, 2, 3, 4. So this dot size minus 1. Good. Now, if somebody magically came along and gave me this function, right, then this would work. We'll assume that we've already done this function. I've offloaded some of the thinking here to later. I don't want to have to think about that. Let's go ahead and put that over here. We'll do that later. That's why that's a classic to do, right? Now that I've got the last node, though, what do I do with it? I had the last node over here. I make it point to a new node. So the next step is going to be to create a new node containing x. Well, let's create the new node first, right? New node t of x, right? Now I make the last node point to this new node. How do I do that? Last dot set next new node. Uh-oh, I don't have a setter, do I? Well, right now I have a very good reason to do so, though. So let's go ahead and add it. There's get next, public void set next node t, and I'll call it node. No, I'll call it next because that's what it is. This dot next is equal to next. There. And now it works over here. Again, generally you want to avoid setters unless you have a very good reason to do so, and now I have a very good reason to do so, right? I want to make sure that I'm linking stuff together to new nodes, new nodes, new nodes. All right? That's it. That's all, right? Yeah. Good job. Good. You're thinking ahead. So what happens if you don't have a head element in the list already? That's why we test. It's going to fail, and we'll come back and fix it. But before we can even test, we do need to do this to do here. How do I get a particular node? So let's come over here and try to think about this. So if it's 0, which element do you want? The head. If it's 1, you want this one. So what you would do is you would start at the head, right? And then you go over here and you get this element, right? And you pull out this, or you actually pull out this entire node and retrieve it. That's one next iteration. This is called a traversal. I'm starting at the head and I'm traversing to the next node. Then I'm traversing to the next node. Then I'm traversing to the next node. 1, 2, 3 traversals to get the 4th one, which is at index 0, 1, 2, 3. So in other words, if you want an element at index I, then how many traversals should you do? I minus 1 traversals, right? Because if it's 0, 0 minus 1, negative 1 traversals, does that make any sense? Nope. So 0, that's probably going to be an edge case, one of those corner cases that we're thinking about. Otherwise, 1 traversal gives you 1. Oops, you know what? I think my number is wrong anyway, right? Yeah. There we go. So I traversals. Why? Because the 0 here, 0 traversals. You just start there. 1 traversal, 2 traversals, 3 traversals. Right? All right. A loop, right? Okay, let's start. Node T. What I'm going to do is I'm going to keep track of the current node. Current. Where do I start? At the head, right? For int I equals 0, I is less than something, I plus plus, traverse. So I'm going to go ahead and traverse by saying that the current node is equal to the current node dot get next, right? Start here. If this is my current node, how do I get to the next one? Get next, right? Update my, what I'm pointing to. How do I go to the next one? Get next, update my pointer, right? My reference. All right. How many times should I do this? Good. Why index? If it's 0, how many, is this loop going to execute? Nope. And so what's your current? The head. What if it's 1? It executes once. So head dot get next gives you the second node, et cetera, et cetera. Now return current. There we go. We're all done. Or we think we are. I'm going to kick this down to only 10 here, right? And I'm going to, we think we're done, right? But we're not. So I'm going to go ahead and insert, say, I times 10. There we go. At, actually, no, let me go ahead and just add it to the end because that's what I implemented, right? Dot add element. I plus 1 times 10. There we go. Run this. It's going to, oh, there. We've got our first null pointer exception. Okay. Why? Because last is null. Okay. Fine. Let's go ahead and set a breakpoint and let's walk through this. All right, so I is 0 here. What's in the linked list right now? Yeah, the head is null. The size is 0. Okay, let's go ahead and step over. Step into. Okay. Oops, no, I didn't want that. Come on. There we go. Step into, yeah, there we go. All right. So X here is 10, the first thing that I need to insert. So we're going to actually get the last node. Uh-oh. What's the last node if I step into that? Are there any nodes right now? Remember this, the head is null. So current is going to end up being null. And when I step over that, this will not end up executing, right? And it will return current. Okay, so last now is null. Why? Because it's an empty list. This will work. We can create a new node, but then last dot set next. Because last is null, are we going to be able to set its next element? Nope. So let's stop this process here and think about a corner case here. When you want to add an element to an empty list, that's like initializing a new head. So if this dot size is equal to 0, then what I do is I create a new node, and I simply say this dot head is equal to new node. And that's it. Right? If the list is empty, it's pointing to null. Head right here, my head is pointing to null. All I'm doing is creating a new node and pointing to it so that now I have that one element. I should also return, right? So that I don't do this code down here. Hey, wait a second, I've got some repeated code. Let's take this, put it at the top, take away that, there we go, and immediately return. Okay, what else? Size. What do I need to do now? This dot, I've added something, right? Size plus plus. Right. Now, if I did that here, oops, undo, there we go. If I did that here or here, doesn't matter. But if I do it down there, what do I need to make sure that I do? Do it in there. Right? So I'm just going to do it in one location here.
You do it up there, wouldn't that mean this head would never get set?
Oh, good point. That'll screw up our get node down here, won't it? So maybe now we do have an argument for doing it here and then here. There. I like that better. Let's go ahead and see if this runs. Crossing my finger here. Hey, it ran. Did it work? I don't know.
It didn't crash.
It didn't crash. If that's your only if that's your only criteria, then we're done. Right? But it's not. Let's go ahead and take a look at this through a debugger. Right? So the size is 10. 10 things got in there. That looks good. What about the head? The head has an element 10. Head is pointing to next, which has an element 20, which has an element next pointing to 30, pointing to 40, 50, 60. In fact, this debugger right here is a visualization of your linked list. Right? There's the first one, there's the second one, third one, fourth one, dot, dot, dot. And it's just going to go ahead and keep indenting here. 60, next, et cetera, et cetera. All right? So that's nice, but I kind of want to print it out just like I printed out the other list, right? So let's go ahead and do that now. Down here, public string toString. There we go. All right. I want to make sure that I've got 10, 20, 30, 40, 50, all the way up to 100 here. System.out.println, numbers. Numbers. There we go. And right now it's not returning anything because of, it's not compiling, that's why. But now I actually need to return something. I'm going to go ahead and have a string builder here. And what I want to do is I want to go through each one of those nodes, and for the first node, second node, third node, fourth node, et cetera, et cetera. Right? And I'm going to go ahead and append it to this string builder here, so that I return sb.toString. Okay. Well, I do know how many nodes are in there, right? Size, because I'm keeping track of that. So I could go with a formal, just a regular old for loop, right? But I'm going to go ahead and go into a while loop to get some practice, because eventually we're going to have a bunch of while loops on this stuff, because we're going to iterate over over elements in the linked list. All right, so I need a current node. Node key current is equal to this dot head, because you start at the head. Right? While you are not at the end of the list, right, what I'm going to do is I'm going to concatenate, or append the current node's element, and then go traverse to the next node. Yeah, go ahead.
When you say that you're at the end of the group, you mean you're not currently at the panel?
Exactly.
Currently pointing to the
Well, that's a good point.
because if
So if we start here, we want to append 42. Go to the next one, append 20. 10, append 20, append 101. When we go over here, we don't want to append null, right? At that point, though, we break out of the loop, right? So if I'm keeping track of a current node, initially that's the head, and then I move that over. Actually, you know what?
wouldn't you need to break the loop before you print the tail?
Well, I mean, just append. You'd want to include the tail, though, right?
I mean, in case if you're using commas or something.
Oh, okay. So yeah, if you want to format it, I'll worry about formatting later, right? So initially, we'll go ahead and have point it to head, point it to the second one, point it to the third one, point it to the next one, and when it points to null, that's when we know that we're done, unless we want to do some fancy appending here. So how do I know that I'm not at the end of the list? Well, that red mark there that I was using was keeping it current. while current is not equal to null. Right? When it hits null, then I will break out of this while loop and return whatever string I've built up to this point. Okay? Oops, come on. There we go. So let's append the current node's element. sb.append and what is it? Current.get element. And then we'll append a comma space. Right? We will have that superfluous Oxford comma, coding Oxford comma at the end, but we won't worry about that just now. Then traverse to the next. I guess if you also want.
An Oxford comma, I think.
Well, a coding Oxford comma is, right? If we have analogies to grammar and sentences and paragraphs in code, we can have analogies to the Oxford comma as well, right? So there's the append traverse to the next node. Right? How do I do that? Current is equal to current dot get next. There. Let's see if this works. It does. Right? And I should have put an end-line character there. Right? So 10, 20, and there's our coding Oxford comma, right? That last one there. Do we care about it? I don't know. Do you care about it? Is it bothering you enough that we should? Okay, well, let's take care of it, because actually I wanted to take care of it because it illustrates what we're going to do. All right. I don't want to know when I'm at the when I've fallen off the end of the list. I want to know when I'm about to fall off the end of the list. So while current.getNext, if I'm at the end here, right? I don't want to append this. Instead, I want to jump out of the loop and append it down here without a comma. So while the current dot get next is not equal to null, that's how I'm going to go. That's how I'm going to know that I'm about to fall off the edge of the list, but I'm not actually going to fall off of it. That way down here, I can go ahead and append current dot get element. Good. Oh, well, sorry. Yes. Thank you. There we go. All right. Let's see if it works, first of all, and then we'll improve it. Hey, that coding Oxford comma is now gone. There's got to be a better way to express this, right? Current.getNext is not equal to null. Parsing that out, I mean, we know what it is because we just wrote it. But if we come back here like a month from now and read it, current.getNext is not equal to null. What does that mean? It means that the next node of the current node is not, so I must be at the last element of the list. Let's go ahead and put that into the node class here. I like that. Public Boolean has next. So, Mr. Node, do you have a next element? True or false? If this dot next is not equal to null, then I will return true. Right? Otherwise, if it is equal to null, else return false. Right? We'll come back and improve this as well, but come over here. Now I can remove this and have something that makes a little bit more sense. Current dot has next. While the current node has another neighbor to go to, go ahead and concatenate this and then traverse to the next node. Right? The second that you are at the last node and there's nobody else left to do it, you're not going to concatenate it. You're going to jump out of this loop and then concatenate it. All right, we've refactored it. Let's make sure that we do some regression testing. Still works, but it's a little bit cleaner code, right? While the current has next, right? That's way easier to read, right? Instead of null stuff. Now let's come over here and improve this. If this condition true, else return false. Is there a better way of doing that? Return just the expression. If that expression ends up being true, you return true. If that expression ends up being false, you return false. So just return the expression. That's it. Simpler code is always better code, and usually 90% of better code. I need to think about edge cases again. It worked because I printed it at the end. What if I print it before anything happens? What if I print it after, each time after I do this? Uh-oh, null pointer exception. Before I even get started, it's happening right here at line 13. An edge case for if there's nothing in there. So let's go ahead and say if this dot size or this dot is empty, right? Because I already implemented that, return empty, just like I did before. And then I don't end up doing any of that stuff down there. Run that again, and now everything works. It's empty, then it's got 10, 20, 30, 40, all the way up to 100. Everything works now. Awesome. So I've got a lot more work to do here though, right? Add element, remove last element, get element at index. Actually, do I have a lot of work? No, because I had some forethought here. Remember? Get node. If you can get the ith node, the index node, can you get the element at that index? Absolutely. Node t index node, indexed node is equal to this dot get node of index. And all I need to do is return indexed node dot get element. That's it. Because I wrote this one general function to rule them all. And I'm doing everything else in terms of that one function. Careful. Am I allowed to get any arbitrary node? Integer x is equal to numbers dot get element at index -10. Is that going to work? I mean, it shouldn't. Let's find out what happens. Oh, it does. 10? Is that what's at index 10, -10? No, right? We've got, there's no such thing as index -10. So let's find out what's going on here. What I'm going to do is, oh, no, I don't want that. I want a breakpoint right here. Let's come back over here and let's examine what's going on there. Okay? So, oh, I've already got that. So step over that, step over that, step over that, step over that, but it'll step into this. So you're asking for the element at index 10. Let's figure out what's going on there by jumping into that function, right? So index here is -10. Get the node at an index -10. The current is equal to the head, right? So when I step over that, the current is now equal to, the element is equal to 10. Am I going to iterate on this for loop here? For I equals 0, I is less than index, which is -10? Nope. So this loop will not execute, but what do we end up returning? The head. Okay. So that's why we're getting 10. Let's come back over here and fix it. Get node's fine, right? What was wrong was not checking that their index was correct. So if index is less than 0, or index is greater than this dot size, this is the same exact stuff we did yesterday, or on Tuesday. We'll throw a new illegal argument exception, invalid index, plus index. And if we're going to be doing that over and over again, maybe we want to put that into a function. Right. Now when I do this over here, I'm going to get the proper exception. No, you can't do that, -10. You can't do 100. Why? Because, well, there are only like 11 things in there, or 10 things in there, right? Let's see if it works for, say, 0, though. 0 is at, 10 is at 0. That works. Give me something else that we should try. What about 3? That should be 30, right? Or 40, right? 0, 1, 2, 3. What about that last guy right there? What index should he be at? 9. And we should get back 100. That looks good. If I go up to 10, I immediately have that exception. Excellent. All right. Get size is empty are all done. Ooh, replace element at index. That's going to be easy too, right? All what you need to do is what? Same stuff up here, get the node. Right? Oops, come on, there we go. First of all, check to make sure that their index is correct. Here's the index node, right? And we'll go ahead and replace indexed node's element with, oh no, sorry, sorry. This is not what I want to do yet. Return null. Where was replace? This is the one I wanted. Sorry, I started cutting and pasting in the wrong location. There we go. So index node dot get element. No, I want to replace the element. Replace indexed node element with x. Okay. Indexed node dot set element to x. Don't have that. Okay, let's go ahead and do it then. Set, not next, but set element. We have maybe a very good reason to do so now. Set element, and it's going to be a void function. And we'll take an element of type t, element, and we will say that this element is equal to that element. Oh, so now we have a reason to do that. Okay. Let's re-examine that reason. Right? Maybe I don't want to do that. Maybe I want to protect that element and make it final. Is there an alternative way of doing it? Now that would work, right? That would be perfectly fine, right? So let's think about this. Oops, sorry. Let's make a new list here. It's 10, 20, and 30. Okay, so I want to replace 20 with 42. One way that I can do that is the way that we were trying to do that, by simply erasing that and putting in 42 without changing the structure of my list. What's an alternative? Make a new node with 42, and then make 10.2 that new node. Where should that new node point to? Okay, I like that. What happens then to that middle node? Exactly, it gets deleted by garbage collection. In fact, this looks like insert too. So maybe we could kill two birds with one stone here by implementing this this way, right? Okay. Well, let's go ahead and backtrack on this first of all, and let's see how we did that first. All right. So I created a new node. That's easy enough. Let's do that step really quick. So create a new node. Node t new node is equal to new node of x. There we go. There's my new node. Now, what do I need to be able to make 10.242 and 42.2 that one? Well, you need these two nodes, right? Yes. So you can get this node. We just did that. Next. How do I get this previous though? Can I go backwards? Not the way that I've designed it. That's called a doubly linked list, and if you want to do that, that's perfectly fine too. But for now, can I go back? No. But what if I got this node, right? And then I could always get the next one. I could always get the next one. Right? So let's get this node instead. Right? And let's call it what it is, previous at index -1. Right? Node t current is equal to previous dot next, and node t next is equal to current dot get next. I have all three of those now. Right? With one call to this get node up here. Now, you do have to be careful because there are edge cases. What happens when it's empty, right? Well, you can't replace it, so this would have thrown an exception here. What happens when there is no next element? What happens when there's no next element, right? That you end up replacing the tail. Right? So think about those, but let's go ahead and finish this up, just not thinking about those. Right? How do we go about this? Previous, or here, let's outline this. Previous needs to point to new node. New node needs to point to where? Next. Right? And then current, do we care about it? No. Nope. It was only serving us to get this one right here. So previous needs to point to new node. Previous dot set next to new node. New node dot set next to next. There you go. Okay. And I'll return. Well, now I do need current, right? Because remember we redesigned this so that we would actually return what you were replacing. So return current dot get element. All right, let's test this. Over here in demo, I'm not going to get an element at index. I'm going to replace element. Let's just go ahead and replace something that we think is probably going to be safe. We'll replace whatever is at index 4. And then let's go ahead and run this. So what was at index 4? 0, 1, 2, 3, 4. We got 50 back. And what does the list look like after we've replaced it? 42. Good. Always be testing your edge cases. What happens when we try to replace the element at index 0? Did it work? Yep, at 1. What happens when we try to replace the element at the tail? Oh, that worked. All right. What happens when we try to replace an element before we even have anything in there? Oops. Duplicate, there we go. Thank you. All right. Null pointer exception. All right. That's not what we should be getting back. What happens when we try to replace an element right after we insert it, right? So those are the edge cases that we'll need to think about, and we'll pick it up there on Tuesday. Any questions? I don't know, are there any questions? There were no questions online. Is there anybody watching? No, there is not. Okay. You're an audience of one today.